Good afternoon, gentlemen. I am Tad, and this is Mahika. We are from Group 2, and our project is mechanical energy harvesting using piezoelectric zinc oxide nanowires. So today's world is full of problems, and we as engineers strive to come up with solutions every day for these problems. But as engineers, we also know that one of the most important factors in decision making is to prioritize. So the big question here is, what is the #1 problem in the world? Now, experts have always differed in opinion, but according to Nobel laureate Richard Smalley, the greatest challenge in the next 50 years is energy. So solar cells, windmills, turbines, these technologies have been around for decades, and we have successfully been able to harness a good amount of energy from the sun, water, and wind. But what about ourselves, human beings? Human beings are active creatures, always on the move. Especially when we're talking about hardworking individuals like you and I, we're talking about a large amount of mechanical energy that is going untapped every second. So when we first came up with our project, our main objective was to address this exact issue and come up with a lightweight, portable, comfortable energy harvester which can be integrated into our daily activities. Now, in order to harness this energy, we have chosen a technology well known today as piezoelectricity. Without going too much into the technical detail, piezoelectricity is simply the electric charge that accumulates in a certain solid material in response to applied mechanical stress. And for our design project, we have chosen zinc oxide. Why zinc oxide? Because it has one of the highest piezoelectric coefficients. And as engineers, we all like bigger numbers. So just to give you a brief idea about our masterpiece, this is how it would look if you zoomed into it sideways. So at the bottom, we have our flexible pen substrate coated with silicon nitride for added sturdity, on top of which we have our bottom chromium electrode. And the light blue region that you see here is our zinc oxide nanowires, our piezoelectric layer, and on top of which sits the top electrode and a PDMS layer for insulation. So where do we plan on integrating this device? Imagine if you could simply type on your keyboard and your typing would charge your laptop in real time. Imagine if you could charge your phone or iPod from the energy of your heel strikes. The possibilities are endless, and the limit is your own imagination. And now, I'll hand over to Mahika to talk about the specific details of our device and what we have been able to do so far.
Perfect. Thanks, Dad, for the great introduction. And now I would like to talk about some of the design considerations that we made and the journey that has been so far to come up to our final device. So again, being engineers, we did start off with modeling our device. So the plots that you see here are just zinc oxide films, like bulk films. And the graph on the left shows how the displacement profile would look for the zinc oxide film when it experiences a force of approximately 36 Newton, which is what we estimated is the amount of force that an average male's heel strike generates. And then the plot on the right shows what kind of a potential plot it would generate on the entire zinc oxide film. So we can see that from the plot that the simulation tells us that we can, with this kind of structure, we can almost achieve a little over 2 volts, which is what we started off as our benchmark. And then moving on to some nanowires, since that is what we wanted to explore more for a device, we tried to simulate how could the length of nanowires affect the resultant output that we would get due to piezoelectricity. So we simulated a 2 and 4 micron length of nanowires, and we kept the number of wires to 10. And we observed that longer wires would give us a higher output. And again, even in literature review, we've seen people work with piezo zinc oxide nanowires and how they could tune its properties by changing the size. So before I get into the nitty-gritty of our design considerations, I would just like to give a brief overview of what our fabrication process is. So we do start with a flexible pen substrate, which is just a polyester, and it has great barrier properties. The next step is to deposit silicon nitride using sputtering. And the main purpose of this layer is to provide it some sturdiness so that we can get a uniform growth of our wires. But at the same time, we're not really sacrificing the flexibility of this device. The third layer is our bottom chromium electrode, on which the zinc oxide seed layer is deposited, which is key for the growth of our nanowires, for which we use the hydrothermal mechanism to grow the nanowires. And then lastly, we complete the device by using an aluminum-coated PDMS layer as the top insulation, as well as the top electrode. And that is what gives us our final device. So as I'd mentioned, we considered a lot of different factors to reach at our final device. And the three main factors that we considered were substrate, which seed layer to use for the growth mechanism, and the final structure, the piezoelectric element of the device. So the substrate, we were debating between whether we wanted to go rigid or flexible. And so we went ahead and we tried on silicon and glass as well as pen, and we grew some nanowires. So the images here show that in terms of the growth, we got a pretty uniform and pretty similar growths on both the substrates. And the reason why we went ahead with the flexible one is because it can conform better. It would probably be more durable than something like glass or silicon. And with new manufacturing technologies like R2R and printing coming up, we could possibly see this being easy to manufacture in the future. The next consideration was our seed layer, which is key for the growth of the nanowires because these act as nucleation sites from which the wires crystallize and grow. So for this method, we had two approaches that we could have used. One was just spin coating some zinc oxide nanoparticles, and the other was actually RF sputtering a thin seed layer of zinc oxide. So again, we tried both to see which one would work better for our device. And as the images show here, the sputtered zinc oxide seed layer gave us much vertical and uniform and a dense growth of wires. And then even the results reflected that. We exposed both the devices to a mechanical stress by tapping on them, and we measured what electrical results we would get. And it was evident that the device, which was made with the nanoparticle zinc oxide, gave us much lower results than the sputtered seed layer. And the third factor that we considered was the structure. So we wanted to see whether a hybrid device would give us more output and more durability of the device, or just nanowires. So we considered that as well. We went and we made both. But with testing and with working with the device, we observed that the zinc oxide nanowires device only gave us increased flexibility, durability, and there was almost no difference in the output that we got for both the devices. So why nanowires only and not the bulk zinc oxide film? Well, we can think of nanowires as basically a disintegrated zinc oxide film, which we propose that would provide more flexibility and durability to the device. So again, even here we saw numbers, and definitely the nanowires only device was a clear winner. So just to summarize all the design considerations and what we ended up optimizing was we used a flexible pen substrate, we used a sputtered zinc oxide seed layer for growing the nanowires, and we used the nanowires only structure. And now I would like to move it on to Tad to talk about our characterization and testing.
Thank you, Mahika. So in order to characterize our device, as Mahika had mentioned earlier, first we've used some SEM techniques to first confirm that we're actually getting some growth of nanowires. So once we confirmed that, we moved into the electrical testing, and here we will show a small demonstration of that. One second. I think this crashed.
Okay. Does it let me?
It's crashed.
It's taking a while
Sorry
to
about
load.
that, just not responding.
Seriously.
Yes.
It's not letting us.
Can you just kill the PowerPoint and try to restart?
Didn't you try? You tried it yesterday.
Yes, we've tested this before.
Oh,
Yes, there we go. So the first video is demonstration of the keyboard that we're trying to simulate, and we have our device underneath. And upon tapping, we're expecting to see a potential difference across the oscilloscope. We don't have any sound. Was supposed to be sound here. So as you can see, there are spikes upon tapping. And next we'll be showing you a video where we've actually lit up an LED
This is not.
using our device.
This is.
It's not letting us scroll forward. Just wait.
So you can see the blinking happening of the LED.
Yeah, there we go. You can see a blink in the LED. So as you can see, we were successfully able to light up the LED, which actually required an approximate forward voltage of around 2 volts. And this is not only proving that our device is producing a potential difference, it's also flowing current through this diode. In other words, we are creating power. So to reinstate this, we have actually done some current measurements across a 1 ohm resistor using the circuit setup shown here. So as we tap, the current flows across the resistor, let's say clockwise, and then when we release, it flows anti-clockwise or vice versa. Channel 1 in the oscilloscope measures the potential at the top node, while channel 2 measures the potential at the bottom node, and the difference in these two potentials is the potential difference across the resistor. And using the known value of the resistor, and using Ohm's law, of course, we can calculate the current flowing through it. And according to this setup, it was observed that our device is producing around 40 milliwatts of power, 200 milliamps of current, at an efficiency of around 5.5%, assuming that the force of each keystroke is from an average individual and not someone as strong as Professor Nasser. So a summary of our design and results. Here's things to wrap things up. This is the big picture. On the left, we have our design considerations and the changes we have made to our design in order to achieve these higher results. On the right-hand side, we have our 3 primary goals that we initially started with and how we have successfully able to achieve them. So first of all, about being comfortable. It's made with soft polymer interfaces, so that makes it comfortable and can be easily integrated into wearables. It's portable, as our average device can easily fit on the surface of our palm. Good things always come in small packages. And it's light. It's approximately 0.3 grams, which is 10 times lighter than a penny. An object 10 times lighter than a penny being able to produce 40 milliwatts of power. Is this science or is this magic? But this is not where it ends. And like every other electronic device, there's always ways to improve it and take things further. And some of the few things that we would like to investigate are the following. For now, the device needs wires, but can this be integrated into e-textiles and other wearable electronics? The force that we're exerting on this device, what if we could have layers of multiple of these devices and the force could be exerted on all of them, kind of like a stat design? We are generating current in real time, but what if we could store this and use it later? And last but not least, what if we could dope the zinc oxide nanowires to increase its conductivity and get even bigger numbers? But given the scope of our project, this is as far as we have been able to achieve. I hope you're all impressed and ready to give us some amazing remarks. Thank you for listening, and please do visit our booth. If you have any questions, please.
Great. Q&A, yeah.
Any questions, sir?
You don't get away without.
Oh, yes, yes.
Okay, so why is longer better? Well, first of all, what's your capping layer?
I'm sorry?
Your two electrodes are connected top and bottom.
Yes.
Right.
Okay, and what's your capping layer then?
PDMS
Okay, but
at the top.
what's your conductive?
It's the zinc oxide nanowires. That's basically the piezoelectric element, which is basically conducting through the electrodes into the wires.
Okay, so if this is my zinc oxide coated surface,
Right.
I've got a conductive base. That
I
Right.
have two electrodes on top and bottom.
I
Yeah.
connect one wire here, but if I've got zinc oxide here,
Mm-hmm.
your zinc oxide is not something I typically think of as being conductive.
That's why we have
No,
aluminum on
we
top.
have aluminum on
Okay,
top.
So you're putting aluminum
Yes,
top, you're
yes.
sputtering it. And
Yeah, it's sputtered on the PDMS. So the PDMS, aluminum coated PDMS acts as for two purposes. So it's electrode.
Yes.
Yeah,
Okay, so now you've got that coating.
right.
Why is longer better?
So basically, we've seen that piezoelectricity depends on the conformity of the structure of the zinc oxide crystals, right? And it's an asymmetric crystal. Now, if you have if force is being exerted on, let's say, this much of an area, it's basically the polarization will be higher if it's the force will be exerted on more zinc oxide atoms if it's longer. It's not just on one single area. So if you think of it longer, it's exerting on a higher number of atoms instead of just flat.
So there's a lot of protocols. I'll pass it on to my two colleagues here in a second, but a lot of protocols involved in this. So who
Right.
developed what?
So we have started from scratch, literally from the pen flexible substrate, right?
You
And
still had an RF sputtering system.
Right.
You had a zinc oxide target.
Right.
You had a procedure for doing the deposition.
yes.
Here's a
So
suggested deposition rate.
previously, there have been research has shown that they can do zinc oxide films,
Yeah.
and we've used the hydrothermal growth. They've used the hydrothermal growth for the films. We've used a similar kind of technique for the nanowires. So we have kind of tweaked our design, played around with our parameters, and see what works best for us. And we've finally come up with this final.
But the whole
device.
design process, we started with something that we took inspiration from literature, and we started with something, but along the way, given the results that we were getting, we optimized and we tried to work through
Okay,
it. So,
you read some papers,
right.
but this was in the G2N.
Yes.
Yes, this was G2N.
G2N, did they have a standard process that you were using? Or did you come in and say, I need to develop this kind of process, and you then developed the process?
Second one.
That's very impressive. You have to say that.
Yes.
Especially in a job interview.
Okay.
Right?
Yes.
You'll remember this, right?
Yes, for
Right,
sure.
right.
That's important.
We came
Right.
up with that and we proposed, and then our consultant gave us all approval to
Okay,
G2N.
that shows that you drove this.
Yes.
Right.
That's really important,
Thank you.
Right.
especially in an interview.
Okay.
Right.
Okay, good stuff.
Thank you, sir.
Yes.
So
Okay.
I'm done. I've carried away. Sorry.
Sir.
So I have a simple question.
Yes.
Mm-hmm.
Say you made several different samples with increasing nanowire length.
Mhm.
What overall trend would you see with respect to the potential difference? I assume this is in plane.
Right.
So
Mhm.
Right.
You say the longer the nanowire, the better.
Yes.
Yeah.
What does that mean? What trends? Have you
This-
seen this in literature?
Yes,
Right.
it doubles.
With doubling the
we've
length.
seen that it actually doubles with the length, but then here's another thing.
Oh.
Longer.
Sorry, I asked for a trend.
It's a linear.
Doubles with the, yeah, thank you.
It's a linear trend. Yes, that's what it is.
We're going into mad level.
Well, no, it's a linear.
It's a linear trend.
Yes, it's
That's what simulations show
So
to us.
why did you choose the length that you chose? Why
Yes,
not?
so-
From an engineering design perspective,
Yes.
Right.
because this was not well communicated in your presentation.
Okay.
Right.
You made many decisions.
Right.
What was that decision process? Once you got the protocol developed,
Right.
which is very impressive, why are you using this film versus
Okay.
another?
So our
Right.
sputtering actually has a growth rate of 0.5 microns per hour, right? And we have spent 6 hours to 8 hours in the lab. So we thought a faster process would be electrochemical deposition, but the electrochemical deposition in the university is not working. The machine doesn't work. So we've stuck to this traditional form, and the reason why we stuck to maximum of 3 microns, longer the better, but longer also means less durable because it will tend to break. So we have come to the point that 3 microns takes around, let's say, 6 to 8 hours. That's an optimal time for one device. We don't want to be spending weeks on one device. That's why we stuck to the, yeah, but then if we could move into electrochemical deposition, that would be way faster and we could probably go longer and more devices in less
But
time.
then we need to do a durability study and determine what the optimal. I mean,
Yes.
there's an engineering problem here. Infinite
Right.
would make sense with respect to
Right.
potential,
Exactly.
but I could break that very easily.
Exactly.
Right. I mean, there has to be a limit for
Exactly.
sure.
It goes back to
for sure.
durability as well, with
Okay,
trade-offs.
last very quick question. Are you sure that you are dealing with, so zinc oxide, a film, is it just piezoelectric?
Mm-hmm. The reason why we think it is and not flexoelectric is
Yeah.
because we have also tried like shear forces.
Yeah.
And shear forces does give numbers, but then it's also breaking our nanowires. So you can maybe we can argue that it's flexoelectric, but then it does not serve the purpose of our device. So we can't call it flexoelectric at the same time when it's breaking, right? So we're saying that it's vertical displacement instead of just shear.
Okay, but am I flexing this board?
No, that's no.
That's just shear.
That is
Now I'm
flexing.
flexing.
Now you're
Yeah.
flexing.
Okay, so I think you're misunderstanding. There are different modes of shear.
Okay.
Right?
That's flex.
Fine, thank you.
All right. Thank you.
One last question.
Yes.
When you're applying the normal stress,
Right.
what do you think is happening to your rods? Is it just uniaxial compression or are they bending around?
I think they're bending.
They're bending, but
They-
then at the same time, basically what happens is when you exert the force, it deforms the crystal, right? And it creates the polarization, let's say plus minus. That's
Is there
pretty.
difference? Is the primary mechanism your compression or is it bending?
No, it's compression. It's definitely
Compression.
yes. It's definitely compression
How can you guys be sure?
because the force that we're exerting is vertical. We're not actually
Yeah,
Yeah.
that's if you have it's basically a vertical beam, right?
right.
If you apply normal force, even there's a slight displacement,
Mm-hmm.
it's going to bend.
Mm-hmm.
Correct.
And even they are vertical,
Mhm.
they're still a little bit of off axis.
Right. Right.
So
So according to
But
our-
it might be limited given that how dense the growth is, there isn't a lot of interwire distance as well. So it could be a combination of two as well, bending and,
right.
it
Then
could be a combination.
Given that the FASM images that we have seen, they've actually looked pretty dense and we don't see it in a bending form.
do you think there will be a difference in response if the primary mode is bending compared to compression?
I think
We've
there
tried
would
actually
be.
flexing it and there's give us lesser numbers than actually tapping
Yeah,
it.
there would be a difference because it's all
Because it's-
about.
Sorry, let her finish.
Yes, please.
Because it's all about the direction, because it's all directional, like the piezoelectric coefficients as well, they're all directional, right? So I think this versus this would be different, would give different results.
If you do this, you're positive and negative here. If you do this,
Right.
you're positive and negative.
If we do this,
If you bend it around,
right, it would still be along the wire, but I feel the distribution would be different though, I feel, overall. Yeah. Okay.
Thank you.
Great, thank you. Yeah, sure.
Can you go back to the slide with the circuit testing when you have your piezoelectric resistance model? How did you calculate the efficiency?
Oh, the efficiency has nothing to do with the circuit. Efficiency was based on if we have a 30 Newton force, we calculated the displacement on our device. Force times distance equals to energy transferred. Per second, we calculated how much per second we're basically, the power that we're exerting, that divided by the power, basically that's our max that we're exerting, right? Input. And our output is 40 milliwatts. So our input divided by output times 100%.
Your power output is going to be changed if you change the resistance.
Yes, it will. So this is across a 1 ohm resistor.
Yes, but I mean if your resistance comparable to the piezoelectric resistance, all your current calculation is going to be different.
Yes, there will be. But then it depends. So, but then if you use
In
a
this case, your efficiency is not going to be consistent.
yes, that's why we said the efficiency is based on the results of a 1 ohm resistor. So if you use a higher resistance, we didn't have any current flow through it. It was too high.
This is crashing.
You good to go?
Okay,
Thank
thank you.